Slope stabilization. Slopes may be stabilized by one or more of: number 1, modifying the slope profile where possible; number 2, supporting or anchoring the existing profile; number 3, improving or draining the slope material. Profile modification. Added material below neutral line, also removal from above, increase stability. Neutral line is where a slab surface is horizontal below undrained slide, displaced to where depth of slab surface is equal to pi in drained state. Berm ledges, about 5 meters wide on steps 10 meters high, redistribute, lower and stabilize circular slabs in weak rocks. Small failures on steep faces of steps land on berms harmlessly. Hanging blocks, slabs and wedges which rest on daylighting, unfavorably oriented fractures can be removed, may leave asymmetrical road cuttings in beds with depth greater than pi. Toe weight. Toe weight is effective, especially where lower end of slab surface turns up, may be mass concrete, rock fill, earth bank reinforced with geogrids, or thick crib walls. Size must restrain formation of new under-riding slab surface reaching beneath new toe. Unloading head of slide generally has less effect. Original cause of failure should be removed where possible: riverbank erosion control or seawall to prevent toe removal. Drainage of slides. Poor water pressure is critical to slide stability, so drainage is usually very effective and is the only economical method to stabilize large slides in natural slopes. Surface drains. Concrete diversion ditches intercept surface flows. Drains on slides reduce infiltration. Shallow drains. Stone drains in trenches 1 to 2 meters deep lined with geotextile have limited effect by reducing soil water. Deeper counterfort drains also provide shear resistance. Deep drains, most effective, mined adits with leaky walls and a sealed floor, or boreholes with perforated casings inclined to drain out from slide toe. Relief valve. Drain up or down to aquiclude, need pumping unless drain into lower aquifer. Some London clay slopes have been drained into lower sand through 100 mm boreholes filled with sand and polypropylene tubing on 2 to 5 meter centers. Interception tunnels, cut behind slide to reduce groundwater inflow, used in 1800 to stabilize falling slopes above city of Bath. Impermeable clays respond poorly to normal drainage. Electroosmosis or heating with deducted hot air can improve clay stability but are expensive. This map shows the drainage system to stabilize the slopes. At the top right, you can see the diversion ditch where they have made a ditch to divert the water. And secondly, this is the surface drain in back deep throw, and then pumped relief valve, and it comes down. Surface stone drain on the surface. They have pitched the rock pitched and made the drainage system, and then a tree draining borehole or adits. And here comes relief drain into lower aquifer. They have made a drain system to shift the water to downside aquifer. Slip surface, you can see this is a potential slip surface. Interception tunnel parallel to face. Landoless landslide. The map shows a new road along North Wales coast and the new marine defence works were sited to act as towweight, improving stability of old slide and restraining formation of new underlying slip surface. Stop stabilization. Folkestone Warren landslide, Kent. Multiple rotational coastal landslides in chalk over clay crossed by Maitline Railway. High winter water tables and a relaxation of over-consolidated clay cause renewed movements. Larger slips are triggered by falls from chalk cliffs onto slide head. Toe erosion increased due to beach starvation after harbor wall extended in 1905. Traps longshore drift. On the right side map, it explains stabilization measures placed since 1915, failure, and added to since. Mass concrete toe weight also acts as seawall to reduce toe erosion. Drainage adits cut in from seawall, lower water table. Movements are now reduced to very low rates. Mass support. Number 1. Retaining walls. Common practice and successful on small slopes and cut faces, but not on larger slopes. Large unstable slopes are not easily retained. It is difficult and usually uneconomic to build and found massive retaining walls at the toe of major natural landslides or large unstable slopes. Concrete walls need sound footing, prevent from rotation by buttresses, rock anchors from near top end or base or deep foundation, weave holes to permit drainage. Masonry facing improves appearance. Dental masonry. Hike out weak zone of rock and refill with cemented masonry or concrete with stone facing may dwell into rock. Gabion walls, cheap to install, can retain soil slopes and act as toe weight. Separate concrete or shotcrete may be used with rock bolts as in tunnel supporting, spray over bolted reinforcing mesh, or use fibercrete containing 50 mm length of steel wire within the sprayed mix to give tensile strength. Ground improvement. Vegetation. Cover reduces rainwater infiltration and a root mat provides tensile strength in soil but is destructive on rock faces as roots force open joints. Geotextile. Geogrids or wire mesh anchored to bolts, fixes surface and catches small stone fall. Plants grow through and provide long-term strength. Biodegradable jute mesh provides short-term support. Weathering protection by separate concrete or fibercrete or by separate mortar. Any cover must have drain holes. Pattern bolting creates thick stable layer by tightening the natural rock joints and also reduces water infiltration. Grouting. Grouting fractured rock is expensive and rarely applied. May use to stabilize secrete. Liming. Liming clays reduces plasticity, improve unstable sodium montmorillonite by change to calcium variety. The cross-sectional map shows the different stabilization methods of the slopes. From top to bottom, you can see reinforced earth, gabion wall, suspended netting, and dental masonry. Here you can say anchor walls. The length of the anchors varies depend upon the condition of the rock. Reinforced shotcrete. Pattern bolting is the different patterns you can use to anchor in the rock slopes. Rock trap. Ground anchors. Tensile support may be provided to oppose directly the landslide driving force. Rock bolts. Steel bars 25 mm diameter, 3 to 10 meter long, in drill holes fixed at inner and by resin or expansion shell. 100 kN load. Tension to 60 kN. Main purpose to increase normal stress across joints cannot be placed in heavily shattered rock. Isolated support bolts to retain individual blocks of rock. Grouted dowels. Steel bars in drill holes through joints provide direct shear resistance. Board piles. Act as large dowels, but limited success. Concrete piles, 6 meter long, 1.2 meter diameter, placed across slip surface of Portuguese bend landslide. Los Angeles had no major effect. Some rotated, some sheared, slide float around others. Rock anchors. Multiple steel cables, 10 to 40 meter long, in ribbed protective casing for installation in drilled 100 mm holes, up to 2000 kN load, tension to 60%. Fixed length about 5 meter resin, bounded into rock, provide tensile support and tightened rock fractures. Most effective were installed at angle of F above slip plane. Anchored walls, flexible or rigid, distribute load from anchor caps onto weak landslide material. Slope stabilization. Hard edge cutting. Shallow slide initiated during construction of Penang motorway, stabilized by lowered profile and the rock buttress. Subsequent movement required anchored wall. Crushed rock in geotextile faced with shotcrete with 41 cable anchors, each 1000 kN, spaced 1 to 3 meter, bounded for 6 meter into stable sandstone. On the right side, shear case. may be used to stabilize toes of slides in weak soils. Trenches filled with the granular material with high pi reach through slab surface into stable ground.